back that up. How you doing, Aim?
I'm okay.
Uh-oh, you look a little subdued. Did you just take the test and Luis just took?
I don't think so, but I do have 2 exams this week, and I'm getting ready for them.
Which classes?
Number theory, and then the capstone course for math for teaching.
Kelly's course, yeah. That sounds like a fun class. She's got lots of.
It is a fun class, but good Lord, it's a ton of homework. Just every assignment takes at least like 8 hours to do.
I agree.
What is she doing? Teaching you graduate algebra or something?
Every question has, okay, explain how you would explain it.
Okay, that's an open question. You could write an encyclopedia on that.
Right. And in a lot of cases, that's what we end up having to do for it to count. So it just takes a long time.
It really
something
does.
About teaching, sometimes you get this educational edu-speak or something, and it gets overwhelming sometimes. They have their own lingo, education professors and stuff, and sometimes it's just overwhelming. Everything's so short and abbreviated, whatever. It's something. I don't think we totally understand how the brain works anyhow. And I think that they're discovering that perhaps people are hardwired different ways, right? So it's hard to, some people are good reading a book. Other people need to have this kind of, dog and pony show. And other people just go on the web, right? And just sort of get a little bit of this and a little of that. All right. Okay. So how many? Oh, we got 16 people. What am I supposed to do today? Gosh, I forget where we were, but there's a bunch of odds and ends to catch in this section of the book to close off chapter 5, and also for me to make your next test. So I thought I'd start with this a problem in the book using my favorite distribution. Unless there's any comment, concern, question. Anybody have questions about the grading of the second midterm? I've had very little feedback from that. I guess I was.
Well, in a way, that's a good thing. It means people either already understand what they did wrong, or they're happy with their grade, or they understand their grade.
You're an optimist, because the way I see it, sometimes people are pissed off and they're hurt because I didn't give enough partial credit, and it's too painful to bring it up, But I'm a reasonable guy, If you felt the partial credit wasn't fair, believe me, you should, come to office hours. But you're optimist. You're an optimist. Did you have a question on the test, or you guys were good with? All right, she's occupied right now.
Oh, our group? No, it's fine. We did look it over. It's like, okay, well, that's fair. The question where we misunderstood what the question was asking, we didn't get credit for. Whatever, big deal. I feel like our grade is fair.
Yeah, I think you did well, but it wasn't perfect. So I thought, I was curious if something but you know what you did wrong, so there's no.
I'm not gonna cry about not getting a perfect grade. It's fine.
Yeah, I've had that before. Somebody had an A+, and they were just melting down about why they didn't get 2 more points of credit.
Good Lord, I'm gonna be done with this class in like 4 weeks. I don't care. So I don't care about this, like getting every single point. What I'm going to remember 4 weeks from now is the lesson stuff that we did. So good. I'm not worried about the grade.
Good. Well, some people just don't get the point. No, okay. Never mind. Okay, so let's warm up with a problem from the book in chapter 5. Hopefully I can do it. Some of these exercises are a little bit tricky. So this is an exercise in book 5.38. And so y is uniform 0, 1, 0, 5 in this case. Now notice it doesn't matter whether I put square brackets or round brackets because of the fact that we're talking about continuous random variables. And this is a sort of a complex question. What is the probability is the probability that both roots of 4x squared plus 4xy plus y plus 2 equals 0. Both roots of that quadratic are real. So it's sort of using different things. Let me make sure I've got this correct. 4x squared plus 4xy plus y plus 2. All right. So how to visualize this? So the y is a continuous random variable. It's a box random variable. Okay. Its density is just, the support is between 0 and 5, and it's just a box. So it could be, the y could be any number in there. So with what proportion of the time, if you choose randomly in there, are the both roots of this real? So how do we do that? So this is a quadratic of what? It's an x, right? So what is the? Can you see this, or maybe okay, 4x squared plus 4x capital Y, y is the random variable plus capital Y plus 2 equals 0. So x equals what? What is the quadratic formula say? I want to be out of the washout, so it's dangerously close here. So x is, where do I need to put it? So x equals negative b minus 4y plus or minus the square root of b squared, which is 16y squared, minus 4ac. 16 and c is y plus 2. And over a, 2 times 4. So what? Assuming I did the quadratic formula correctly, let me just check it. Negative x equals negative b plus or minus the square root of b squared minus 4a. I left something out here. So minus 4ac. 4ac. Okay, looks good. So going back into this this quadratic formula discriminant thing. So they're both going to be real if this is non-negative, right? Are we good with that? Let me just check if I've lost somebody on the chat here. Looks good so far. Okay. So you have real roots under what condition? So real roots, if and only if what? Well, what's going to be, you take out that 16, what are you going to have here? Y squared minus y minus 2. I need that to be non-negative. Okay, so y squared, I'm factoring out the 16 to 4 there. Y squared minus y minus 2. And luckily for us, is everybody following me here? Or maybe somebody came in late. The question is, if y, random variable y is uniform between 0 and 5, what's the probability that this quadratic has real roots? So we can factor this. How does it factor? Okay. So now, again, this is sort of a kind of a long-winded problem, drawn out thing. So, but this is a review of pre-calc, right? So, where is this going to be negative, and where is it going to be positive?
It's going to be positive from negative to negative 1, negative from negative 1 to 2.
Slow down just a little bit.
Sure.
So you have, we only have to concern ourselves, okay.
That's true. We only have to concern ourselves with things that are greater than 0,
Okay,
but still.
So if we go below negative 1.
It's positive.
this will be negative, obviously, and this will be negative, so it's positive here. And we go to 2. If we go between 1 and 2, it's negative, right? And this is probably positive over here. So it seems that, if I get this right, it seems like it's between.
So we need real solutions. So we need the square root to be positive. So from 2 to 5.
Okay, but this is the y. So the y goes from 0 to this. This is 0, right? So yeah. So okay, right. So between 0 and 2, it's negative. It's no good. But between 2 and 5, it's where it is good. But what proportion of? So what's the probability that we land between 2 and 5? So I want the probability that 2 is less than y less than equal to 5. What is that? 3. Well, looks like 3/5. Because this in totality, this is 5 and this is 0. So 1, 2, 3, 4. So from here to here, we have positive roots. But what proportion of that? This is a uniform distribution, so it's 3 over 5. 60% or something. That's what I'm getting. I think you did it. I think Aim did it already. But I mean, does that make sense? Or if you want to do it in terms of an integral or something like that, you would have to integrate the density function from which is what? It's 1/5 from 2 to 5. But I don't know that it's necessary. That's why I like these problems.
Not necessary, no, but I did it anyway. I'm a definitions person, so it's like, okay, well, the definition of finding the area, it's finding the area under a curve, so I'll just make an integral. But
the area under a curve, good.
You don't need it,
especially when the area they're dealing with, if it's a joint distribution, so 2 variables, then it's a region. Mm-hmm. And then you can use your geometry to get, like if it's a trapezoid,
right.
Geometry to get the area when it's better, than trying to get out the limits, figuring out the
absolutely.
Limits. So yeah, that has come up in the past. That's interesting that brought up. Okay, well this was just a little warm up, but I thought it was clever though. He's trying to mix in a few things here. Mm-hmm. Well, hold on, let me find the next thing I was going to do. Yeah, I should at least. I don't want to overwhelm us with. I should check the chat here. Chat looks good. But we've touched on a few things. The most interesting thing in here that would be the normal approximation to the binomial. To me, that's the most interesting. But when I speak about the normal distribution, we know it's a weird curve, and it has a weird, but it's got sort of a complicated density function, okay? And what is that density function? So if x is normal, and so it's a 2-parameter thing. In the book, they write sigma squared, but in most stat books I've seen, they just write sigma for the second parameter, the standard deviation. Standard deviation is the square root of the variance. But Ross has really bought into this variance idea, so he puts a sigma squared. I think he's fighting off all the statisticians. But anyhow, if that's what it is, then its density function, let's see if I can recall it, is 1 over square root of 2 pi sigma e to the minus x minus mu squared over sigma squared. So what kind of things do we notice about this? First of all, it's pretty ugly. Let's see if I have it right. But You see, it has this exponential drop off. So it has this exponential decay, and it's also symmetric about the mean mu, this function here. But it's exponential drop off, so it goes down like exponential decay. And it's what makes it a normal curve is that it comes down quite fast. Has anybody studied stats? You know, the t distributions. The t distributions don't come down as fast. They have more in the wings or in the arms of the more mass in the arms, but the normal comes down. So this is the mean. And the standard deviation, I don't prove this, not today. The standard deviation is to the break point, the inflection point on the curve. But as you can see, there's two parameters, right, for the normal. Can you think of a random variable that only has one parameter? Well, like the Poisson has the parameter lambda, right? And so it kind of gets that lambda from taking n times p in the binomial. So binomial has two parameters of the number of reps and the success probability. So it's got two, but this is an example of two parameters. And as far as what we're supposed to learn, we're supposed to do calculations, normal calculations. Oh, is that big omega? Where is that omega squared? Oh, this sigma. This would be an omega, right? Or this. But this is sigma. That's the standard deviation. This is a sigma. That's a mu right there. I'm sorry if I'm not being clear today. Okay. But okay, so I'm kind of. This is the problem about teaching computer science algorithms. I always look from the big to the small. Whereas if you're a math person, you do lemmas, lemmata is a plural for lemma, and you go to the outside. Yes, sigma. Thank you, Amy. You know how to make that symbol. Good for you. After class, show me how to do that. I don't know. I forgot. It is a lowercase. We're used to calling this sigma, right? So it's a lowercase.
They're both sigma, just upper and lowercase.
Yeah. I've forgotten. Sorry, just whatever.
You're
Shows
fine.
you how little you need to know to do this drama. I actually had a TA when I was an undergraduate. A TA I took whatever it was, third year algebra, and the TA just totally blew the problem set that we were supposed to do, and he just closed the book and said, "You guys, now you know how little I have to know to do this job." I still remember that. Okay, what was I saying? Well, it'd be kind of nice if this was normalized. So normalized means we assume this is the center is 0 because we know it's symmetrical because of this structure right here, right? It depends on the distance from the mean here. That's, so it's the same thing. And you can make this equal to 1. And if you do that, then you get this symbol, which is the symbol for the standard normal density. And there are tables for this. I'm getting a little bit far afield, but I have to. I can't help it. This is what I have to do. So the tables will tell you and we already talked about it, but just for instance, if this is -1, then they'll give you the table in the book will give you the area from -infinity up to -1. That's the CDF area. So this here is a CDF function, normal CDF. So standard normal, unit normal, CDF function. Okay, so let's try. Let me try to. I really should be talking about this, but I feel that's not why I'm here. I got to talk about simple stuff first. But keep this in mind that you can make a change of variable to get where you are. If this is the one you got, you can make a change of variable to become this. So the function that has this CDF is the random variable is called Z. It has a name, and that's a normal with 0 and 1. I don't care about 1 squared because it's 1 here, so it doesn't matter. But if you have this kind of guy, if you have an X guy, and you want to transform it or normalize it into this guy, you can do that. And I think I may have spoken about this before, but you just take x minus its mean over the standard deviation. That's a new random variable. And this, when you make this translation and scaling, you end up with this guy. And all of these, this information here is in the table to do this. So let me just first, before I give the table, let me give you the rule of thumb. I probably already did it, but I'm going to do it again. So the rule of thumb is what? It's actually very good to have this rule of thumb, be thinking about it, because then you can tell if your answer is way off base or not, if you made some mistakes. So let me redraw this standard normal density function. Okay, so obviously this is symmetrical, so to be a density function, you have to have one, but that's hard to do with that weird function, so I'm not doing it at this moment. But so this is half of it's over here, half of it's over here, but if you're within one standard deviation of the mean, the standard normal, then approximately 68% of the area is in this region. If you're moving out to within two standard deviations of the mean, then how much do you have? That's 95% of the. So what you get from this is that, yes, it goes to minus infinity or plus infinity on one side, minus infinity on the other. It goes on forever, but you're not getting much out there. It's like dust. At some point, it's like dust. You're not accumulating much of the area. And if you go out 3, I feel like I'm teaching Math 140, but I can't help but to do this. Okay, if you go out 3, then, so between here and here is 99.7% of the observations. Okay, why does this matter? Well, there's an example in the book about grading on the curve. And to be honest with you, I'm sorry, it's been so long, I don't even remember what it is. I had to read the book. And I don't even know that people do that anymore, but I guess some do. And they try to fit, they fit the scores into a normal. They figure out what mean would, in standard deviation, a normal curve would normal random variable would generate their distribution, their histogram that they got. So, and I didn't know what that was, but let's take a look. So if you're grading on the curve, it turns out that now I'm going to need to do something else. So if you're grading on the curve, these guys, if I recall correctly, if you're here or over, these guys get A's. This is going to have to, so let me just double check it. And B, so if you're here, that's the B range. And if you're here, that's the C range, the D range. And if you're below this, so if you're over in this range, that's the fail. Maybe I'm failing to describe this. Has anybody encountered this? I mean, this is like old school grading. If people encounter teachers that grade on the curve by this, something like this?
This is exactly how my physics professor would do it.
Well, okay, then it's not a relic of the deep past, you know. But the question is,
yeah, he would just, everything would be graded based on standard deviation and mean, and well, every test. So his grade was completely based on tests. And each test he would calculate the average, and then that would be the C to B split, and then each standard deviation up from that is a grade up, and each standard deviation down is a grade
I hear
down.
you. I hear you. Okay, let me
And,
just.
and then he would drop our lowest score too.
Okay.
Out of the whole
But
semester.
let's. I'm trying to. Okay, what I'm thinking about is I've had some experience working with being in the company of people who make standardized tests, like the AP exams for high school. Okay, and they were very clear at the beginning of their presentations to say the best problem of a true false question is a problem where half the class will get it wrong and half will get it right. And I felt that was very unfair to do problems where you expect they've been structured so that through various things, right? Distractive information in there or wording that's kind of tricky or whatever, that it would be 50 wrong and 50 right. What is their purpose? Why do they think it's so important to have problems of that nature where 50% get it right and 50% don't? What do you think the reason is? Okay, because you're dealing with a binomial distribution, right, with probability of success of half. Well, it turns out that if you have enough problems, you're going to if the problems have that property that half will get it right, half wrong, then you get a beautiful normal curve out of that. Okay, that's the goal. And because they always want to find, again, this is just the fixation they have, but they rule the universe, right? These people, standardized tests rule the universe for students wanting to get into good colleges, perceived to be good colleges. So that's the purpose. And I don't know if you've ever seen this situation, but there's a pegboard, and down here there's trays. And okay, the ball is dropped and it hits this peg and it's 50-50 going either way. When it gets to here, it's 50-50 either way. And I saw an exhibit like there used to be one at the Museum of Science and Industry where it took 2 hours for them to drop balls. They must have dropped, 100,000 or something. And this is enormous 2-story pegboard. And yes, at the end of the thing, it was a perfect normal distribution. And that's a simulation, but it was perfect.
That's cool.
This is a physical representation of it, and with a 50-50, right? So it comes down 50-50 here, and it pops out of this, and then it hits the next line of pegs 50-50 to the left or right of that. So this is why they want that. But okay, so not to take too much time with this, but how many people get A's? So approximately, okay, if you're using this rule of thumb, this was the example in the book. How many people are getting A's here?
16%, right? About.
Yeah, well, let's check it out. So what is the rule that we're trying to employ? 68, 95, 99.7% rule. So if we're trying to employ that rule, so that you have 6. Okay, so half of this is 32, right? Half of this. So this slot is about 34%. 34 plus this. Now this is symmetrical. That's 50. It's 50%, right? So 34 plus 50 is 84, right? So yes, this guy is giving more than, how many A's is he giving? You're following 16% A's, right? Approximate. Right? You want me to do that again? Is anybody confused by, let me check the chat. So how do we know that it's 16%? Well, this slot right here, so it's between 0 and 1, you're going to have 34% of the observation approximately. Now you have to add all of this, and that's 50%. So this 50 plus 34 is 84. So that means the complement, this all has to be 1, would be 16%, okay? We're doing this approximate.
Cool.
So we got that. So how many people get B's? Well, what's the percentage of the B's? Well, that should be clear, right?
So it was half of the 68.
Yeah.
So 34.
34. And it gets complicated at some point here. So how about the C's?
Same as the B's.
What about these D's here?
That's symmetrical with the A's, except you're subtracting part of it. So So that's within
it's
95%.
It's 16%. Okay, you're right. So it's 16%, but you don't have this tail. So according to this, how much tail is there? Well, let's see. This whole amount is 99.7, right? So I'm trying to get the D right. Uh-oh.
Well, I think the easiest way is to take 100, or not 100. Actually, just like we could take the 95 and subtract 68 from it and divide that by 2. Or you could take
Yeah,
I
okay,
did.
I'm sorry, yeah,
the thing
it's
with the A
95,
that I was mentioning.
It's 95 minus.
But yeah,
Okay, let's hold on a second. What is this? Should be simple. What is my D range here? I'm getting a D on this right now. So like this. So
the first way that I thought of was 95 minus 68, and then you subtract that
it's
from, or yeah, that's it. That's basically it. You divide that by 2.
by 2. So you take 95 minus 68. So that gives me this, and divide by 2, right?
Mm-hmm.
So what is it? 7. What divided by 2? 13.5. So it's approximately 14. So it's 13 point something. So 2. Half of this is what? 13.5.
Yeah, I should.
So the answer is 13.5.
I just did it another way too. So that
depends on how you want to. I want round figures here. So 13. I'm going to round down or round up. Neither, because this doesn't look right either way. So about 13.5. And what about this fail range here? So what is this?
That's what's left. So that's 100 minus 95 divided by 2, so 2.5%.
Right. Well, it's 0.3. So shouldn't it be? If 99.7, there's 0.3, right?
But that's only. But fail is.
That's for the 3. Yeah.
So we're going out here, right?
It's 2.5.
Yeah.
Oh, from this. Okay, so it's you have 2.5 on either.
Yeah, going out to infinity.
So yeah, it's 2.5. So you're gonna add. So it's 2.5%, right? It's 2.5 because this is 95. So 5% has to be shared between. It's 2.5. So 2.5% will fail, right? Okay, I hope I did it right. I guess there's nothing. I didn't need this.
Not for this particular thing, no.
I didn't need it at this point. But anyhow, I didn't know that this was the way, I don't think I've ever had a teacher that does. When I was a student, I didn't have anybody that I knew was grading on a curve. But the good thing about it is that they're forcing sort of a certain fraction of the people to get A's. Whereas I definitely have had teachers that didn't give any A's. So in a way, it's sort of a guaranteed. If you're grading on a curve, somebody will get an A there.
So given any student's score, there's like a 2.5% chance that it's going to be above, like a high A, like above 100% kind of thing.
You mean, okay, so.
Well, if your scale is like, depends on how you set up the scale, but if you said
with 2 standard deviations, it's not extraordinary, right? I mean,
mm-hmm.
If you're 6 standard deviations up, that's extraordinary. Getting into Da Vinci.
I just realized how, because I remember a few times getting a score that was like higher than 2 standard deviations by a little bit, and I just realized now how impressive that is.
Well, that puts you okay. Well, where does it put you? If you're higher than 2 standard, do we do it? I mean,
that is.
You're 2. It looks like you're 2.5% of only 2.5% of the people land in there.
Yeah.
So that is impressive. But then again, I don't trust these standardized. I don't completely trust people. Prep. Yeah. They have prep programs for them, so I don't. You don't have people taking them cold. Like I'm sure if Albert Einstein took a. Speaking of Albert Einstein, he had I had caved in and went to the Wikipedia on the Pythagorean theorem. he has a proof in there, and there's like 130 proofs of it. Some of them are very, very, very tricky, I think. Okay, I got to do a little work here, and I don't know where to start or where to turn. But it's supposed to do the mean and standard deviation of the uniform distribution, but I don't want to do it. Let's do a problem for the book. Just a calculation to make sure we can use the table. Okay, this is just a fail-safe check to make sure we can use the table in the book, because we haven't done that yet. So example 4b. So x is normal. What parameters does it have here? Mu is 3, and the variance is 9. And they want you to compute the probability that x is between 2 and 5. This should be easy enough. Got to get my glasses here to see this. Okay, so in order to use the CDF table in the book, what do we need to do? I need to get this into a standard normal distribution, right? So what is the transformation that I was telling you to do? You want to you subtract the mean and divide by the standard deviation. Well, that's the square root of the variance. And that will standardize this. And so 5 minus 3, we have to do this. So this is asking for, what is the probability that the standard normal, a random variable, lands between minus 1/3 and 2/3? Okay? Now you might say, this is easy, just look it up in the stupid table. Well, the table is, wants you to think a little bit, okay? Not just punch a button. So what is involved here? This is 0. Okay, so 1/3 is like about here, and 2/3 is here. Okay, so all we have is information of the CDF, in other words, the accumulated area from minus infinity up to. So let's shade in what we want here. How are we going to do this? Well, there's two different things here. So how to do it? So if you just go up to 2/3, you get all of this stuff. So we don't want everything. So let's break this down. I need a little space here. So what we now have in front of us is 1/3, the probability of 1/3. Let's include a standard normal less than 2/3. Okay, so we could go. We could get this. This is how I see this. Okay, look at this line right here. So to get that, we could take a half minus. So you could go. To get the strip right here, even though I need this stuff in addition, so we could go, this is 1/3. So you could go 2 times phi of 1/3 minus 0.5, and that's getting me this strip. Here's my blue. Okay, so this part here is maybe I did this one. So this, okay, 2 times phi of 1/3 minus a half gives me this amount right here. Double will give me this. But what about this section? So to get this, I could just go phi of 2/3 minus phi of 1/3. This is probably not the most efficient way to do this, but okay. So that's giving me this blue. I should have written it in blue. Okay, so what's doing a little algebra on this first? So we have 2 times phi of 1/3. And here I'm subtracting off, so it looks like it's going to be 1 phi of 1/3. Okay, canceling this, minus 0.5 plus phi of 2/3. Okay, let me check the chat to make sure everybody's still awake. Okay, again, phi of 2/3 minus phi of 1/3. So that would give me the blue section. And then the other section is this, 2 times phi of 1/3 minus 0.5. 0.5 is all this. So you do this in algebra here, so it's minus phi of 1/3, so it's phi of 1/3 and 2 minus 1, it's this minus 0.5 plus this. How do we now use the table? Well, the table is not that accurate, but 1/3 we can look at as 0.33. So there's this table on page 170, which I expect you to use on the test, okay? Not just to, I want to make sure you can read these tables. So to look up phi of 1/3, that's 0.33, 0.6293. Okay, minus half. What's phi of 2/3? Well, that'd be 0.67. .779, okay, 0.7486. What's that equal to? It better be the right thing. I'll be very disappointed if it's not, but I mean, this is just I'm doing this because we'll have to do this. Minus 0.5 equals plus 0.74. It better not be bigger than 1. I get 0.8779. Ah. What did I do wrong?
So you didn't subtract. So
Really?
phi of 2/3 is all the way from the tail up to 2/3. So a better way to think
No,
about
I did. I
is
subtracted right here.
okay.
I did right here, right?
Phi of 2/3 minus phi of 1/3. Okay, that's right there.
Right. So that gives me this is the blue. This is a blue section. Okay.
Okay.
Right. And now the red section
Is phi of 1/3
minus a half. That would just give me half of this. And I double that.
minus 0.5. Let me think of it. Oh, you didn't distribute the 2.
Thank you. Thank you. Thank you. Okay, so if I distribute the 2, what do I get?
I think that should be it.
So it's minus 1. So it should be less. Oh my gosh. Hold on. Okay, so 0.6293 minus 1 plus 0.7486, 0.3779, 0.3779. Okay. Thank you, Hayne. It's a nice save there. I owe you one. Okay, now you know I'm not just copying out of notes. Okay, so this is now that we're now experts on using the table. We can do one of these approximation problems in normal approximation. So the one I want to do is what's the one I want to do? flip a coin 40 times. Okay, so let's do this. This is more interesting than this. Okay, so let me check the chat. No, the chat's clear. Okay, so we're gonna flip a coin 40 times. So 40 times. So toss 40 times. So it's a binomial. Say it's a fair coin. So 40 trials, 1/2. And we want the probability that we get exactly 20 heads. So you want to approximate. So this is x. Approximate the probability that x equals 20. All right. Okay. So what do we need to do to make this normal approximation? So this x is discrete, and we're going to approximate with the normal. So where do we do this? So we've already talked about this, but the binomial, especially when you get larger numbers like n equals 40, it starts looking very normal-like. So you're somewhere in the middle, but this is, you want to know that for binomial, but you want to do this by, okay, what was that approximation formula that we had last time? So, darn it.
I thought the idea was to just find the mean and the standard deviation and then use the normal.
Yes, right.
Okay.
Right, but why does that work? I mean, I'm relying on what theorem is what I'm saying. You're right, so I'm relying on what theorem. I really need to, this is a math part of me who has to get the theorem. So A, the probability that A is less than Sn minus mean NP, is the mean, over the square root of NP times 1 minus P is less than or equal to B. This is approximately standard normal of B minus standard normal of A. So yes, what I got to do now is I have to standardize this sum here. So, but you need, the problem is you need a region to get, like, okay, if this is 19 and this is 21, I need to take, this is exaggeration, but I need to take a region of the normal curve. You understand? I can't just take, at 20 I would get 0. So what's the process here? This is called the continuity correction. So you go from 19.5 to 20.5, and you look at this, and that's the area that I want to take. Okay, so this probability that we want will be close to this area of the curve. Okay, so how to do it? How to do this? So I want the probability that. So now I've still got the x. So start with 19.5 less than or equal to x less than or equal to 20.5. Hopefully I'm not in the washout. Just barely not. Okay, so now to make this, I need to normalize this. Okay, this is still a standard. This is still a binomial random variable here. But notice I can't just do it at 20. I mean, it would work for binomial, but when you make the approximation, I need a range. I need a region. Okay, so what do I do? Now we can do what Hank is talking about. I've got to standardize this. So what's NP in this case? What's the mean? What's the binomial mean? Well, the mean is n times p. N was 40 and p was a half, so this is 20. So we're gonna have to go 19.5 minus 20, x minus 20. Do everything, and this will be 20.5 minus 20. Now I have to divide by, when it says divide by, is the square root of np times 1 minus p. What is that? Well, in this case, okay, so this, what is this thing right here? So this is the square root of np. np is 20 times 1 minus p, that's 1 minus a half, is a half. So that's the square root of 10. So this thing right here is the square root of 10. This is sort of a complex thing. I hope maybe this is too computational to try to present this. But anyhow, this is what it is. Okay, so what do we know about this? Well, this expression is probably close, because n is large, to phi of b minus phi of a. Okay, and that will be our approximation. So now I have to go back to the table. I've got to do some calculation now and get back to the table. So what is this? Luckily, it's symmetric, right? So, but what is this number? Okay, so I'm going to use this. I'm going to put phi of this, phi of this minus phi of this. Okay, what is that number? Whatever it is, it's the same. It's common on both sides. So I have minus 0.5 over the square root of 10, whatever that is. So 0.5 over the square root of 10.
Call it 0.16.
Approximately, yeah.
0.158.
Let's just call it point, yes. Thank you. Let's just call it, so this is the probability of minus 0.16. Now at this point, I've made the switch over to the normal. So less than equal to 0.16. What is this equal to? Oh, now we're back into another normal calculation. So I hope it's easier than the last one. So this is 0, and this is very close to the center. So, okay, so how will we do this one now? Let's see if I learned anything from the last time. So if I get one of these columns, I can just multiply by 2. So it looks like this is going to be, that expression right here should be equal to 2 times what? Phi of 0.16 minus a half, or 0.5. Is everybody in agreement with that? So this phi up to 0, so all the way up to 0 would be a half. So to get the blue column, it's phi of 0.16 minus a half. What do we get as an answer for this? I don't know. What is phi of 0.16? I've got to go to the table. 0.5636. 0.56. What did I just say? Oh my gosh, here's my table. 0.16. 0.5636. 5636. What is this equal to now? So this is 2 times 0.0636. What is that double? So what are we supposed to get here?
0.1272, I think.
It looks like it's going to be right? 12, 7, 12. Okay, so it's
Okay, I was right.
looks like 0.1272. Okay, now this is one of those crappy kind of problems from the point of view of utility, because you only wanted the probability that x equals 20, but you know what? It's much better if it's a range. Why? Because if it's a range, you can't do all those binomial calculations. That's when you really need this approximation. Because it was just one point, we can evaluate this. We can figure it out to see how good this is. You understand? This is a bad example. He's done this more than one time. Because if you're a student looking at this for the first time, you don't know what's the point. Just use the binomial. It's a one-shot calculation. Yeah, but it'd be a lot different if you go from 20 to 29, right? That would be a different story. So anyhow, what is the calculation, the binomial calculation? What is the binomial calculation? So, let's check it. Check for accuracy. So you have probably that x equals 20. It's going to be what? What is that formula? We should know this cold now. N is what in this case? And what is P? So probably success is a half, and probably a failure is also this. So, well, what is it going to be? It's this rather large number divided by what? 2 to the 40, which is the humongous number. And so I guess an argument can be made that if you don't have any way of, if this is big over big, right? And that could, depending on your precision, you might not be able to do this. But I think my calculator can handle this.
Mm-hmm. So I'm sorry, what's phi again?
What is which?
What's the
this?
Yeah, phi. What are we?
That's the standard normal CDF function. So it's the accumulation from the left, from minus infinity up to 0.16 under the density curve. You understand what this is? Okay, let me just. You notice?
Okay, so that's 0.16 standard deviations, like everything from the left up to 0.16.
Exactly. Right.
Okay.
So if you're gonna
0 being in the middle. Okay.
0, yeah. And so 0.16 is really close, right? So it's something like, the picture would look something like this. Everything to the left. This is phi of 0.16. Okay, I don't know. I should pull my calculator out. Cheaper scientific calculators can't do this, but if you have a smarter calculator, I guess, or something more recent within the last 30 years, then it'll somehow, it knows what to do here. It can cancel it out. But what is it? What do we get from this?
You get 0.1254.
But how did you do it?
By putting in 40, choose 20 in my calculator and dividing by 2 to the doing 0.5 to the 40.
You understand, of course, that this is infinity over infinity. For all intents and purposes,
Yes, but my phone can do it, so I'm happy.
The phone did it, and that's impressive. I got something to 0.1254. Yeah, 0.1254. Just what we're talking about it, because you guys are really sharp, definitely sharper than me today. But if you have a calculator or something, and you have e to the, it wants to calculate e squared or e to the 2.5 or e to the, the 4, something like that. Do you know how that happens? What do they teach you in calculus?
There are 2 ways to approximate e, one with the Taylor series and one with like 1 plus 1 over n to the n.
Oh, that's just theoretical. That's really slow. You could try it.
Yeah, I think they
One
use
plus one
Right.
greater than
The Taylor series is much faster in terms of how quickly it approximates E. I know that much.
Look, I would be a worse teacher than I am
Yeah,
if I
they use
didn't
the
tell you.
first few terms of it, I think.
This Taylor, they always say, oh, the Taylor series for E converges real quick. And why does it converge real quick? CVS, why does it converge? Because of these factorials in the bottom, right? However, this is a lie that they teach you in calculus. They tell you, oh, well, you can approximate nicely with this. Yeah, but that's a lie. That's not how it's done. It's done by something called rational approximation. There are rational functions that approximate e to the x really well. Rational is some polynomial over another polynomial. That's a whole area of research, but that's how it's all done. I mean, it's not done by plug into the Taylor series. No. Because you might have to take this quite a ways to get the precision you want. Rational functions zip in, get it onto it really quickly. They use it for everything, sine, cosine, everything. Well, of course, sine and cosine are built into this, but for everything, logarithm, everything. It's a rational function approximation. This is a lie. That this is. I mean, you need this representation to prove that E is transcendental, right? Or forget about that it's irrational, right? I don't know. Do they teach that in calculus? And to prove this is an irrational number, you need this. It's in the book. It's in the calculus book. But, if you don't have that, you can't touch the rationality of it. Everybody understands that a transcendental number is, right? It's not the root of a polynomial. It is not the root of a polynomial. It's transcendental. With an algebraic, with the polynomial with what kind of, oh my gosh, we'll forget it. It's been too long since I took it. Does somebody know?
And all of this stuff. What does irrational mean again?
Oh, okay.
Can't be represented.
One
as
thing,
fractions, right?
Look, here's a polynomial, right?
So is a transcendental number the same thing, or like where's the overlap?
Well, look. What's the root for this? Square root 2, right? So this means that the number is algebraic. It's not transcendental. How do you prove it's irrational? Well, that's the Greeks wrestle with that, right?
Mm-hmm.
I mean, it's a simple. I mean, I'm sure that Abe did it in Kelly's class, right? It must have done
100 times, yeah, and in a whole bunch of different classes.
Mm-hmm.
It's very important.
Well, okay, if you did all that, and I did all that too, and then one day I was looking in the book for 320, and I was humbled, completely humbled, because they asked the question was, are there numbers where irrational to irrational to an irrational could be rational? That was the question, because is that ever possible? And it's wild kind of reasoning, but it's in the 320 book.
Wow.
I mean, they look at.
So, like, to the power of an irrational number?
Yeah, they're looking at. I'll probably get fired doing these things, but anyhow, so they look at it like, well, that's an irrational number, right? So the question is, the question, maybe you can help me with this because I'm a little bit.
I don't know. I've never seen this before.
Well,
I've seen some weird questions where you have lots of like irrationals of irrationals, and you end up with a rational number. I've seen that, but not to the power of. This is new to me.
Well, the question. Okay, so I think that
I've seen this on a YouTube video somewhere.
Oh, good! You have good retention of things you've seen. I probably saw the same video and I have no knowledge of it. But anyhow, so I think the question was, is it possible to have an irrational to an irrational being rational? And they used simple logic to show that it would, but the logic, it does not give you it does not decisively tell you an example. Okay, so
it proves that it could happen, but it doesn't give you an example.
Yes, but okay. So if you look at this case, so what are the two possibilities? I mean, if this was, suppose it was rational, okay, then what? Suppose it was rational. Then what it's been accomplished? I mean, if it is rational, then you have an example, right? Square root 2 to the square root 2 that's irrational to irrational is irrational, right? So you're done. I mean, so then okay. So if this is not rational, so the only other possibility is this is what? Irrational, right? If I spelled it right. So this is irrational. Okay, but are you following me here? It's only two possibilities, right? Square root 2 to the square root 2 is either rational, and when we're done, or it's irrational. Okay.
Mm-hmm.
So what's the kicker?
And you have to test all the other infinitely many numbers there are.
But no, if they can come up with so they're trying to say that it can happen that it's irrational to an irrational could be rational, right? They're trying to show that can happen, that it does happen, okay? But they're not going to give you the example. So what do I have? What material do I have here to establish that fact that it's true? There's the case where an irrational to an irrational is irrational. Let me blow my nose real quick. Okay, if you see, this is one of those things. When you see,
Is this
you
like?
get really humbled.
Hold on, wait.
You
After
got
this, take that and say, okay, well, if it's rational, you're done. If it's
Yes,
irrational, take it to the power of the square root of 2 again. Because then you're going to multiply the exponents.
So what are you going to do here again? You're going to take square root 2 to the square root of 2, right? But you're going to do what?
Take that and put it to the square root of 2.
You take, and then what do the rules of exponents tell you this is?
You can multiply those two exponents.
Oh,
Can you
cool.
say that again, Ethan? That's what I said when I first saw this.
Oh, shit.
Why doesn't it nail down the example? Why doesn't it nail down the example?
Not quite as satisfying because we haven't said for a fact whether square root of 2 to the square root of 2 is rational or irrational.
It either is or is. So what is it saying? It said either this is rational. If it's not,
And yeah,
this one will be rational. This example will be rational. So it doesn't tell you which. You get it? They both could be.
so the end result
It doesn't tell you which.
okay, so after you raise it to the square root of 2 twice, it's definitely rational, but then
Oh no! See, this would be your.
but we don't know whether the intermediate was or not.
Okay, so if this is irrational, you can take that to the square root of 2, and now you have an irrational to an irrational is rational. The thing is, it doesn't tell you which one it is. Is it this one, or is it this new one over here? It's one or the other. You can't have both. Maybe you can have both, but it's one or the other for sure. But you don't know, so you don't have in your
Well,
hand.
you have to have if it is the first one, then it has to be both because that's 2. 2 is rational.
Then you haven't proved anything. See, if you've done this, you haven't really. I don't think you proved. No, because you don't know if that's rational. Now I have rational to. You wanted irrational to an irrational is rational. Okay.
Yeah, but now we know that it has to be.
Oh, Ethan's right. I see what he's saying.
I might
wait.
not be very clear
Yeah,
now, but yeah.
Okay. Yeah, so we're saying square root of 2 to the square root of 2 is rational. So if you assume that that's rational and then you put it to the square root of 2 again,
They're both rational.
either way they're both rational.
And if it's irrational and then you put it to the power
Okay.
to the square root of 2, then
Okay. Yeah, I see what you're saying. So you
2
can
is
put
rational.
If this is rational,
That was where it first happened.
But we don't have. Okay. What I guess what I'm trying to say is, do you understand? We don't know. We don't have
Whether
for
square
sure
root of
an
2
example.
Power of square root of 2 is rational or not. Still, I get you.
Well, we don't have an example. We just don't have an example of irrational. Irrational is rational. We don't have it. This is what kind of proof? You guys should know this if you've taken the Kelly's class. This is a certain kind of proof. It doesn't tell you what something is, but it tells you it.
Tell
What
you
kind of proof
that
is
it is true. Yeah.
It starts with E and ends with E.
Existence? No.
Camus, Albert Camus. Existential.
Oh, I don't think I've heard of an existential proof.
No, it's an existence proof.
Okay.
It's not a memory. This is an existence proof. It's showing you that there are cases.
Oh wait, I was right.
Yeah, Ethan did say that, but yeah.
It doesn't supply. It's not an example. It just tells you that there is an example. Okay, I sorry if I blew this presentation, but that's it's one or the other.
That's really interesting, actually.
Don't know which one. Don't know one or the other. Okay, let me check my time and see if I can squeeze in one more thing. I got 3 minutes. Let me see if there's anything interesting. Well, what I haven't done is shown if you guys remember your Math 250, I haven't shown that this density function is, how are we going to show this as a probability density function? E to the minus x minus mu squared over 2 sigma squared. Okay, so we want to integrate this, and we want to integrate this thing. And what do we want to get? We want to get 1, right? We want to get 1. So we have to make a substitution. So remember your calculus here? What kind of substitution would be useful here? Let y equals x minus mu over 2 over sigma. Then dy is what? So this would be what? 1 over square root 2 pi. When I'm substituting the dx, I get a sigma which will cancel this sigma. So same limits, but I will get what here? I will get there's something missing here. What am I going to do about that 2? It's e to the minus y squared. I can't do anything about the 2. Let me write that again. E to the minus y squared over 2 dy. E to the minus y squared over 2 dy. Okay, if I make that substitution, then what I have to integrate now is this. So if we can get, you guys follow me? I'm trying to just do basic calculus and stutters and stops. But what do we want this guy to be? We want that to be the square root of 2 pi, right? So if you call this I, then if I showed that I squared was 2 pi, if I squared was 2 pi, then I would get this working out for me. Okay, so do you guys remember the RD theta stuff? Let me check the time. Now minus 1 minute, but let me just lay it down for you so you can work on this. So you're going to let I equal that integral y squared over 2 dy, and I'm going to calculate I squared because what I want is I to be, of course, square root of 2 pi. And if I squared is 2 pi, then I'm in business. So that will be, one of these will be x's, and the other one will be y's. And then you combine them. This is multivariable calculus, so combine them. So e to the minus x squared plus y squared over 2 dx dy. And now you make the polar change of coordinates. So what does that equal? So you're going to integrate the theta from this of e to the minus r squared over 2 r d theta dr. Okay, so and this is a doable integral. Okay, it's sequential. You can do it sequentially, iterated. I'm running out of time, but you can finish this by making another substitution to integrate this. And of course, when you finish all this, you end up with 2 pi. Okay, not surprising because this just has a lot of symmetry in it, circular symmetry. Okay, guys, I'm sorry I had a kind of a rough. I didn't know what to do today. I need to fill in a lot of gaps for chapter 5. Thursday
What's the
maybe.
limits on whenever we change it to polar? It's
Uh,
so from 0 to 2 pi, so all the way around the circle, and then the radius is just as long as it can possibly be. Okay.
Right. The reality of this is, if you could picture it, this double integral, instead of having a normal curve, right, you have, let's say this, you've got something that has circular symmetry. So it's like a flat surface with a bump in it. Okay, right, and it's circularly symmetrical. Do you get that? You can get that volume. You can calculate that volume. It has circular symmetry. So it's like every cross section that goes through the origin is a normal curve, the same normal curve. Okay, so you're kind of reverse engineering this. You're going to get this volume and figure out what the cross section had to be to achieve that volume with that symmetry. See, that's how you're going to do this. It's very tricky. I've seen just like the Pythagorean theorem, I've seen numerous proofs of this that don't use the point. There's other ways, the complex analysis proofs to do this. It's not trivial. This is the only use you have for Math 250A, right? Or 250 in 340. Do you guys do Jacobians in 250? Do you remember that? This is something.
Yeah, I'm trying to remember, like, oh yeah, you change the variable, you have to multiply by some kind of like factor to make it so it's there.
Yeah.
And I'm looking it up right now because I'm like, how do you remember that you multiply by r? There's the area expansion factor, which is the determinant of a thing.
The determinant's a Jacobian.
Okay, it's a Jacobian.
That's a Jacobian. So you're actually evaluating this determinant, right? That's the general.
Yeah,
formula.
this is a thing where I need to review it when I actually understand what I'm doing. But it's multiplied by r.
Yeah, but I feel bad today. I wasn't very focused, but I'll try to fill in some of the gaps. This is I'm not so interested in, but I am interested in when you normalize. If you have a normal curve and x is normal with parameters, but if you normalize that, then it comes into a normal with 0 and 1. Okay, that's really critical, and how that happens. So that's important. Maybe I don't know. Maybe I can wrap it up tomorrow. I'm trying to think. We don't need to know. I guess I have to talk about the exponential distribution because it's memoryless, and that should get your interest up. Memory. What do you mean by memory?
Well, yeah. Well, I mean, I saw it in 341, but I will not spoil it for anyone.
It almost sounds like something that some sort of diagnosis in an assisted living list.
But seriously, when I first saw the if you let's actually do it. Let's figure out the expectation and then use conditional probability to find it. Mm-hmm. I'm like, oh my god, it's the same. So yes. I'm not going to spoil it. It's cool.
That is it. Well, it probably it has to do with ease, right? Like if you look at Poisson, the mean and the variance are the same. I mean, it's a certain kind of mathematical sequence, arithmetic sequence that has this self-similarity property or something like that. There's only one sequence that has, I think if it has a memoryless I don't know. But I know for the Poisson, under very loose conditions, there's only one. The Poisson is set. If a distribution has a couple of properties the Poisson has, then it is a Poisson. So this is, some of this stuff's interesting. The memoryless thing it sounds interesting, right? It's and then there was a problem. Okay, there's a problem in the book about. I'm sorry, I'm just going on and on, but there's a very revealing problem about that feature. or example. Whew. Well, I didn't think I would get through this. I got to do it again at 5 o'clock.
So sorry. But yeah. I guess I'll see you Thursday,
Yeah, hopefully I'll be better prepared. Okay.
Professor.
Yeah, thank you.
Thank you.
All right, Ethan. Nice seeing you.
Later.
Later.